Hello everyone. So in the last video we went over softmax and I derived the update rules for softmax. Eventually I will actually have you code these up yourself and do gradient descent using softmax as the final layer with binary cross entropy laws. But now I want to go over what we did in class, where I'm actually going to have Torch do this for us instead. So this is a review of what we did in class, but if you're confused about anything, I think it'll be a good reference. What I'm going to show you is how to use the Torch library in Python to create and collate a dataset. And then we're going to use the Torch pipeline to take the gradients automatically, to do these derivatives for us and to do the update rules in a loop using something called mini-batch gradient descent. So without further ado, let me show you how to set up the data loader for this digits data. So we'll be doing a multi-class classification problem. Actually, as it turns out, this particular dataset, the MNIST dataset, is already baked into Torch. I could simply just load it in directly from Torch with a method, but I would like to go through and show you a little more details about how to set up a Torch dataset. So I'm going to do it from scratch using these digit images that I created, where I actually put all of the digits in a single image that were in the same class. And so this loop here is going through each one of these 10 images and taking out each 28 by 28 digit and then putting them into a big array. And so that's what this did by itself. What I'm going to do now is wrap this inside of a Torch dataset class. I guess I'll call it digits data. And it's going to inherit, it's going to override or inherit from the Torch dataset class. And I don't always want to do this, but what I will do is I will preload all of the data and save it in RAM. Now sometimes your data sets are too big, you don't want to do that, but I'll go ahead and in the constructor I will do that. And I guess one thing I'll specify though is the folder that these digits exist in, because I'm actually going to have a training set and a test set. So I have digits by itself. This folder is the training set. We're going to train our model on that data set, and then we're going to test it on the ones in this folder. There are slightly fewer examples. We're not going to look at these until the model has been finished. We finish gradient descent, then we will look and see how it actually does on new examples. But I'll leave that open so that I can reuse this class for different objects. And so the folder name is something that I'll plug in here. And okay, so what I'll do is basically the same code that I had before. I'm going to fill in this digits array. What I'll do then is I will remember those digits as an instance variable that I can then recall later when I need it. So the two methods that I need in the dataset class, any class that overrides a dataset, I need a method to tell me how many objects there are in the dataset. So in this case, I'm going to sum up the number of digits in each class. So I'll just return sum of length digits, or maybe I'll just say length d for d in digits. So we'll just test this so far. So if I were going to go ahead and say maybe testing data is equal to digits data, and then the folder for that is just digits. It said expected colon and after the init method. Okay, there we go. So if I print the length of this, I get 60,000. Okay, so and that's a nice round number. Gives me confidence I'm doing things properly. That is in fact how many examples there are in the training set. Now what I need to do is create a method to actually index the data set and pull elements out. So that's the getItem special method here. And so what I'll do is, okay, these digits come one after the other. There are 60,000 of them. I'll look through and loop through until I found the array that contains the digit that I want. So this is where I play the trick. I'll say, okay, I'll start off by assuming that the digit is in, y is fine. I'll start off by assuming that the digit is in class 0. And I'll say while the length of the digits that this index is, I guess, less than or equal to the index that I'm looking for. Then I'll say index minus equals length of self dot digits y. So let's say that there were 5,000 zeros and I asked for 6,000, index 6,000, then I'll subtract 5,000 off, straight off the bat. That'll bring me into digit 1, so I'll increment y here. And then once I break out of this loop, I am in the correct list where I can pull out the digit that I want. So now I would finally say x is equal to self dot digits y at that index. Okay. So maybe before we go any further, I'll just test this real quick. I'll return the digit as it is, and I'll test this, and I'll say, okay, how about we look at, and actually I'll return y as well. So maybe I'll say here x, y is equal to testing at index 100. That should be a 0 because there's a bunch of zeros that come first. And let's just make sure it is. Okay, so there's a little 0 there. Let's jump ahead to index 7,000. That is a 1, actually. Let me jump ahead to index 50,000. That is an 8. Okay, so this all seems to be working out okay. So I'm on the right track here, but there is actually something I want to do to format this output a little bit differently. This is currently returning NumPy arrays, but I actually want it to return torch tensors. So one thing I'll do is I will say, okay, actually one thing I need to do is torch tensors are by default 32 bits. So I'm going to cast this as a 32-bit array. I'm also going to flatten it because I would like this to be actually just a 784 by 784 dimensional vector. So I'm going to take each of these rows and put them next to each other into one big vector of all the pixels. And the other thing I'll do is I'll make a one-hot vector with as many elements as there are digits. And I will say y hot at index y is equal to 1. The rest are 0. And actually, let me also make this a float 32. And so then the last thing I need to do is actually say torch.from numpy x, torch.from numpy y. So now when I do this, let's look and see what we get. Make sure it worked. Oh yeah. Yeah, I meant to say torch.from numpy y hot. That's the one hot vector. It's actually a vector there. Okay, so we return something. This, I guess, was supposed to be an 8. Yeah, okay, so then I see the 1 hot on the 8 there. 9 is the last index. Okay, cool, so that seemed to work. Just a note, again, that I've flattened this x, so if I print the shape of it. So torch tensors are a lot like NumPy arrays. So they have a lot of the same things in common, like shape, for example. So here, okay, they're 784. I flattened them. Now, the really powerful thing I can do once I have a data set in this format that's overridden these methods is I can use torch data loaders to collate the data set into what are called mini batches. So here, if I make a data loader, and I'll pass along the data set object that I've created here, and then I'll say, okay, I want to take, let's say, maybe 32 examples at a time, and I will shuffle them. So it will actually randomly shuffle the data set. Actually, let's say 16. It'll randomly shuffle the data set and partition the data set into disjoint batches of size 16. And so what I can say then is, I'll say capital X, capital Y to indicate that I'm actually collating a bunch of things together. If I say capital X, capital Y is equal to next iter loader. And then I look at this and I print x.shape and I print y.shape. Then what I'll see is that it's actually taken 16 examples of digits, each with 784 pixels total. And it's correspondingly taken the 16 one-hot vectors that indicate which class these digits belong to. So if I were to go ahead and plot those, if I were to say plt dot, or I'll just say for I in range x dot shape 0, I'll say plt dot subplot for I plus 1, so I'll plot this in a 4 by 4 grid, and then I'll say plt dot im show, I'll say x slice out the ith example, and Torch has something like reshape called view. I'll say, okay, I want to actually view this as a 28 by 28 thing. I want to unravel it back into an image. And so I look at that, and here's the digits that I pull out. Let me get those numbers out of the way to make it look a little bit nicer. So those are the digits that I pull out. Maybe on the very first one, I'll show what the one-hot vector is as well. Okay, so the one-hot vector on this one is this. It's supposed to be a 6. That looks right. See, notice how I got a completely different batch this time because it's randomized. But if I loop through all the batches, so let's do that. If I loop through all the batches, I'll say for x, y in loader, and let's just count how many batches there are. What I should see is, okay, so it went through all the batches. There are apparently 3,750 batches. If I multiply that number by 16, which is the batch size, I get 60,000. So again, the Torch is going to partition my data set into disjoint batches. And what I'm going to do in a moment is use these batches to do what's known as mini batch gradient descent. Okay, but let me pause here for a moment and let this sink in. So this is how we do the data wrangling part of it. And then next, I'm going to do the training part. So I will create an architecture that matches what I was doing here with the binary cross entropy on top of a linear function followed by just a function, and then we will use Torch to do gradient descent on that. Okay, so let's take a moment and let that sink in.